तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Now it is time to give you a bag of tricks that you can use in order to solve the problems easily. Okay. I am only going to focus on statics of systems of planar rigid bodies. Okay. Let us go to the first trick. So I am going to call it as first trick, trick number 1. Let us say I have a particular rigid body, okay, and I have forces all around and there is a moment. Okay. Let me just draw so that it is easy. Let us say this is F1, F2, F3, there is a moment here. Okay. I have just drawn some moments that may appear on this. I wish to find out the resultant force and moment. One of the important things to know is, one of the problems that we will face is which point should I take in order to find the resultant. The answer is any particular point you can take, there is no difference as such, because every point of this rigid body will be stationary. Okay. So I can arbitrarily choose a point A, find the resultant force F and the resultant moment Ma, so that I can write these two equations. All right. Now some of the points to remember here is, can I, instead of looking at this is force at this particular point is equal to 0 and this is a resultant force, and the moment about this particular point A is equal to 0. Now the question arises, supposing I take some other point and I say, let us say I found out the resultant moment and that is, let us say MB. Okay. Can I add the other equation and say MB equal to 0? Remember, there are two equations that I can find from here, which is x component and y component of resultant force equal to 0, Ma equal to 0. Supposing I say, okay, I am going to take another point here, I know that this point is also stationary and therefore the resultant force is going to be the same, but moment will be different, Mb, and can I add that and say I have the fourth equation? Can I do this? That is the question. The answer to this is very simple. If I look at this particular point B and try to find out the moment, given that this is a resultant of forces at B, it is nothing but Mb is equal to Ma plus the moment of this force with respect to B. Okay. So let us say this is Ra, it is equal to Ra cross F. Okay. Now we already have F is equal to 0, which means this will go to 0, implies this is equal to 0, this is equal to Ma. I already have Ma equal to 0, this means this is equal to 0, or in other words, given that Ma equal to 0 and F equal to 0, the natural result is Mb is equal to 0. So this cannot be an independent equation compared to these two. This is one thing that we have to understand. okay, which automatically means that I will be able to get only 3 independent equations that I can solve. Okay. Now, let us say I have a force on a body, okay, and I seek to find out the 3 equations that are needed in order to solve this problem. Okay. Let us say these are the forces that are acting on this. Like before, we can choose a particular point and go about doing it. We will get F equal to 0, and let us say there is a moment over here, we have ma equal to 0. Okay. Now, if I have to ask this question, can I take, let us say ma equal to 0, and I will choose another point b and say mb equal to 0. These two together, if I take only these 2 equations, is this going to be valid? The answer is not fully. I need to take one more equation, let us say a point here C, and then find out the moment of the resultant force and then set each one of them equal to 0. Can I reproduce the solutions that I get for this? So, or in other words, let me just repeat this. Can I rewrite these set of equations into this set of equations? Okay. The answer is yes, provided if I just connect, let me just erase all this MBMC so that it is easy for you to understand. Provided these points A, B, C that I choose are not collinear and that this resultant force is non-zero. Okay. If it is 0, then what will happen is some of these equations will give 0 equals 0, which is the same that you will get here also. If this resultant force is equal to 0, you will get 0 equals 0, or in other words, if I have to replace an equivalent set of equations, it is possible to use only moment equations, provided you choose 3 points that are not lying on a single line like this. Supposing I take a point here C prime which is collinear, I will find that I will reproduce the equation that I got for B and C, a combination of A and B. Okay. As long as you do this, it is easier. Sometimes it may be beneficial to use these equations compared to these equations. I will show those in the examples. So, let us take a simple example, meaning simply supported beam, let us say. Simply supported usually is given by this. There is a pin support here or a hinge support there and a roller support here. Let us say this length is L, there is a force acting on this, let us call this as P. The aim is to find out the reactions at say A and at B. Okay. We will use the systems of equations that we get from equilibrium equation in order to solve this problem. Okay. So, the first exercise that we have to do is draw the free body of. Remember, this is a single rigid body that we have here. Okay. So, it is not going to be difficult for us to draw the free body of this. Let us say this distance is 2L by 3 and this distance is L by 3. Okay. Removing this, I will have 2 reactions, one reaction like this and the other reaction like this. Let us call this as AY and this as Ax. Another reaction over here, since it is a roller support, it does not restrain movement along x direction, and therefore let us say this is B or By, okay, and this is a force P. So let us examine the number of unknowns. We have Ax is an unknown, Ay is an unknown, By is an unknown. Given P, we need to find out this. How many equations can we generate? There are 3 equations we can generate, which means that we will be able to solve this problem completely. Okay. So let us try to solve this problem. The first exercise is, if you look at this carefully, there are 3 vertical forces. So the next thing that we do usually is examine the type of forces that are present in this particular rigid body. We have 3 vertical forces, there is only one single horizontal force. So the first exercise I can do is I can write the summation of all components on the rigid body along x direction is equal to 0. That implies Ax equal to 0. So the immediate result that I can get. Okay. What is the next step? I could probably go for the net force in the y direction is equal to 0. That will involve Ay and By. This is where we use a simple trick. Instead of going for vertical component being equal to 0 of the net force on this, let us look at any other option. We have the moment equation that is possible. I can take a moment about this particular point, which means it will involve Ay and By because they have a distance from this particular point. But instead, if I take a point here on A or on B, I know that the moment of Ay at A is equal to 0, or if I had taken this particular point, the moment of By is equal to 0 at this point. So I will choose either of these points and write the moment equation. Let me write it over here. So I am going to write sigma or summation of all the moments at this particular point A is equal to 0. It automatically eliminates use of Ay as well as Ax, only P and By will come into picture. Let me take anti-clockwise to be positive. This helps in writing it out clearly. Again, the same exercise is simple. I just hold this, look at what kind of moment this will create. P will try to push it down and therefore will introduce a clockwise rotation. Okay. Anti-clockwise is positive, and this distance I already know is 2L by 3, and therefore it will be minus P times 2L by 3 is the contribution of P for moment at A. The other one is to do with By, and that is at a distance L. I hold again pivot at this particular point A and see what is the direction of contribution of By. It is anti-clockwise like this, and therefore this is plus By times L, and that is equal to 0 because of the condition that the rigid body is stationary. Remember, in this particular case this is known, these are known, which means I can immediately find out what is By. Okay, L will get cancelled and it is nothing but P 2P by 3. Okay. The next step is to find out Ay. I can do using vertical forces equal to 0 or moment about B equal to 0, either one of them will give the answer. But the key point that I am trying to make here is try and find out a point about which you can take a moment in such a way that you have the least number of unknowns that take part in the equation. Okay, if you do that, then it is easier to solve for reactions. Okay, and very simple, if this is 2p by 3 and this is p, the vertical equilibrium will automatically give you Ay equals p by 3, because Ay plus By is equal to p. Okay. Okay, thank you. Now let us look at one more trick or tip that you can use before solving for systems of rigid bodies. Okay. Supposing I have a rigid body, let me just make it a rigid body of this sort, and let us say these are the 2 points, this is A and B, on which some forces are acting. Let us say this is F1, this is F2. Okay. Now, one of the immediate simplifications that can be done as far as this particular rigid body is concerned is, like we did earlier, if you look at it, we have a force here and a force here, and if we want to find out the relationships or to solve for, let us say, F2 or F1, we should take moment about A or moment about B and solve the problem. Okay. So, in this particular case, let us say moment about A is equal to 0 if this has to be stationary. Then what do we get here? We are going to just change this problem a little bit and see whether we can get some simplification. Instead of taking this, let me take a component of this, which is F2x, and a component like this, which is F2y. Okay. Let us look at the moment contribution of these 2 components of this force. The immediate thing that we find is, since this x, let us say x is along this direction, if x were along AB, if I take AB and set that to be x direction, then I know if I take moment about this particular F2x will not take part in the moment. The only force that will take part in the moment is F2y. Okay. And therefore, this will result in, let us say this length is AB, this will result in F2y times AB equals 0, where AB is the length. This automatically means that this is equal to 0. Okay. By similar argument, if I take moment about this, it is possible to show that the horizontal component or the component along AB of F1 is equal to 0. I am sorry, the component along AB, which is F1x and F1y, are the 2 components that we can split, and we can immediately say that this is equal to 0. Okay. Or in other words, I can simplify this as a problem where if this is A and this is B, I will have forces acting on this way and this way. Let us say this is F1, this is F2. If I use horizontal equilibrium along AB, I can write this to be minus F1. Okay, I have used all the 3 equations in order to come up with this particular conclusion. So, in other words, this is equivalent to saying that if I have a body where forces are acting only on two particular points A, B, then the force will act along that line AB, and let us call this as FAB. Okay. Now this body that I am talking about need not be one single direction like this, one straight member like this. I can also, let me draw it over here, I can also have something like this. Let us say this is point B, this is point A. Okay. If I know that the forces are acting only at A and B, I can just connect these two and say that the resultant forces on this particular rigid body will be acting along this direction. Okay. If I have straight member like this, straight body like this, we call this as an axial member. If we have something like this, the conclusion is that it is along AB that the force resultants will be finally acting. Okay. This result is very useful when we come to systems of rigid bodies, and examples of systems of rigid bodies being trusses, beams and so on.